Hey everyone, so this video is going to go over pretty much the main concepts of the stoichiometry unit that you guys are going to need to know for your quiz this Thursday. If we take a look at this next slide, here we have four main definitions, and this video is going to cover how to find each of these four things: the molar mass, percent composition, empirical formula, and the molecular formula. Alright, so basically we start with the molar mass, which is the mass of 1 mole of a substance. So the percent composition now indicates the portion of a mass of a substance that is due to the mass of an individual element in the substance. So if you have a compound with multiple elements, the percent composition tells you how much is in that of that individual element is in that substance. Next we have the empirical formula. This is a throwback. Of a substance shows the simplified ratios of a substance, whereas the molecular formula shows the true ratios of a substance. For example, I will show you guys right here. C2H6 is an example of an actual substance, ethane, and if we simplify to its empirical formula state, we could get it down to CH3. That's the difference between the molecular formula and the empirical formula. Now the first one we're going to start with is the molar mass. And if we see here, I listed the steps in determining the molar mass of a substance. And you basically need to figure out what is the sum of the masses of all the atoms in the formula. So going step by step, you need to figure out how many of each element is in the formula. You need to multiply that number of each element by the rounded atomic mass from the periodic table. So you need to have that periodic table next to you in order to do these problems. And then after that, you add up the total mass of all the elements to get the overall formula mass. So molar mass comes in different names. You might see it as gram formula mass or formula mass. I like to call it molar mass because this pertains for pretty much any kind of substance. So if we take a look at this example substance, aluminum hydroxide, here we can see the breakdown of the number of atoms for aluminum, oxygen, and hydrogen, and its individual atomic masses, which you could find in the periodic table. And after that, you multiply across right here. And then you should get these values. And then after that, you add all of these three numbers up to get 78 grams per mole. So in order to reach 1 mole of aluminum hydroxide, you need 78 grams. That's what it means. Alright, now we're going to go through this example of potassium carbonate. Oops. Alright, let's go back there. Alright, let's select the pen tool, and here we go, potassium carbonate. Here we have 2 potassium atoms, 1 carbon atom, and 3 oxygen atoms. Now you need to look at the periodic table for this atomic mass right here. And if you happen to look at potassium, you should get 39 grams. You might see a decimal there. Don't forget to round to the nearest whole number. Next we have carbon, and there's 12 grams for every carbon. And for oxygen, we have 16 grams. That's an example of rounding up. You might see it as 15.9999 and so forth. You must round it to 16. Next step, multiply across, and you should get 2 times 39 should get you 78. 1 times 12 is 12, and 3 times 16 is 48 grams. Add it all up, and you should get 138 grams per mole. So you need to reach 138 grams of potassium carbonate to reach 1 mole of this substance. That's what it means. Alright, here's another practice, lithium sulfate. So let's practice by listing each of these atoms we have here. We have lithium, we have sulfur, and oxygen. Let's list the number. We have 2 lithium, 1 sulfur, and 4 oxygens. Next, we got to multiply it by the atomic mass. Lithium, we could round up to 7 grams. Sulfur, let's check. You should get 32 for sulfur, and for oxygen, by now you should probably memorize it, 16. Multiply across, and we have 14 here, 32, and 4 times 16 is 64. Okay, next we add it all up. Okay, that is a 0 over here. Bring that 1 over there. 2, 3, it's 5, it's 110 grams per mole. Okay, that's our answer. Now here we have an example of a hydrate, noted by this little thingy over here. Okay, so Mg, Br, hydrogen, and oxygen. Magnesium, here we have 1 of that. Bromine, we have 1 of that as well. Hydrogen here, it's 2 times 6, so you should get 12. And oxygen, there's 6. Okay, let's work backwards. We know there's 16 grams for oxygen, 1 gram for hydrogen. Now we have to check our reference table for magnesium and bromine. And give me a moment. So let's start with bromine. Bromine, we should get 80. That's big. Magnesium, all the way on the other side, we should get 24. All right, next we multiply across. Let's use a different color, 24, 80, 12, and 8 times 12 is 96. Okay, next we add it up. 3, that's 11, 20, 21, 212 grams per mole. Okay, now we know how to do molar mass. Next we're going to go into percent composition. So this is not too bad, if I might say so myself. Percent composition, this is found in reference table T of the reference table. And here I'm going to write it out for you. Mass of the part over mass of the whole times 100. I may not be copying it word for word from the reference table, but it pretty much gives the gist of it. And here are the 3 steps, the main steps. First, you need to determine the mass of each element, so let's break it down by each element. Next, you need to find the formula mass of the entire substance. And next, we need to calculate the percent composition of each element. First, we need to find the mass of each part, find the mass of the whole, mass of part over mass of whole, times 100. That gives us the percent composition. Let's employ that in the next few examples. All right, so here I have it broken down. We have magnesium chlorate. Here we have 1 magnesium. So let's look back at our reference table to remember what is the atomic mass. That's 24 grams. Chlorine, next we have 2 of them. And the atomic mass for chlorine is, we're going to use 35. And oxygen, 16. Multiply across, 24 grams of magnesium, 70 grams of chlorine, and 96 grams of oxygen. So that means we add all of this up for the formula mass. That should get us, okay, I'm just going to do it right here. That's going to be 190 grams per mole. You guys should check with me in case I'm doing anything wrong. All right. Okay, next we got to find the percent composition of each. So here we're going to times 100 by all of them, because we like our percents as big numbers. Okay, magnesium, we're going to take 24 and divide, which is the mass of the part, over the mass of the whole, 190. For chlorine, it's 70 divided by 190. And for oxygen, 96 over 190 equals, okay. I highly suggest you round to the nearest tenth. So we should get about 12.6% for magnesium. 70 divided by 190. We should get 36.8% for chlorine. And then 50.5% for oxygen. Okay. Just to make sure you're getting the right numbers, I highly suggest you add these percentages up and see if they get close to 100. It may not come out perfectly, but if you happen to check, right here we have 99.9% as our total, so that checks out well. So that's our answer for each element. All right, now we're looking for the approximate percent composition of calcium bromide. Okay, so that means we need to break this down into its elements, calcium and bromine. Bromine, sorry. So there's only 1 calcium and 2 bromines. Let's look back at our reference table. After you do a bunch of these problems by now, you should probably have these memorized. Save yourself the struggle. All right, calcium is 40, bromine is 80. Oh, look at that. Pretty close. 40 grams here and 160 grams for a total of 200 grams per mole. That's our gram formula mass. Okay, now the percent compositions. For calcium, we are going to take 100 times mass of the part, which is 40, over the mass of the whole, 200. And then for bromine, 100 times 160 divided by 200 equals, all right, 40 over 200 is about 1/5, so that's 20%. Over here, we should get 80%. Okay, checks out. All right, so now this next section is going to deal with the meat of this unit, mass and mole conversion. So we're going to be looking at how to convert from mass to moles and moles to mass of a given substance. So let's start with this equation, which you can find in your reference table. And I'm going to write my own version of this, where the number of moles is equal to the given mass over the gram formula mass. Okay? So most often for these problems, you're going to be having to solve for this first. That means you need to look for it. From there, you're going to probably be given either one of these, number of moles or given mass, and then you solve for the other. So that's how most of these problems will go. So for example, what is the mass of 2.25 moles of O2? Let's figure out what is the formula mass for O2. So there are 2 oxygens. Let me erase that too. So there are 2 oxygens and each of them is 16, so we should get 32 grams per mole. So that's our molar mass. Now we're going to go use our formula. Number of moles equals given mass over molar mass. So here we're given 0.25 moles. We're solving for the mass, and our molar mass here is 32 grams per mole. So 0.25 times 32 will get us 8 grams. So that's where you should arrive at, 8 grams. All right, next we have here, so let's go through this each step by step. Magnesium, there's only 1 of them. Carbon there's 4 of them. There's 6 hydrogens and 4 oxygens. 16 for oxygen, 1 for hydrogen, 12 for carbon, and let's look back at our reference table for magnesium, and there should be 24. Multiply across. So notice how molar mass always pops up here. You can never do any of these problems without calculating for the molar mass. 64, you add it all up, and you should get, oh boy, should get about 142 grams per mole. So that's now our molar mass. Now using our formula, we have 2 moles equals mass over 142 grams per mole. So let's see here. Let's analyze this for a moment. We need 142 grams to reach 1 mole. Now if we have 2 moles, we should have double the mass. And if we look at our equation, it should follow through. So 2 times 142, we should get 284 grams for a substance. That makes sense. Next example, what is the total mass of 2 moles of argon? So argon here, how many grams do we have for every mole of argon? So let's look it up in the reference table. Argon. All right, so there are 40 grams per mole of argon. So we have 2 moles of that. Well, gee whiz, guys. What do you think this number will come out to? I think it's going to be 80 grams. All right, now we're going to look at the reverse here, going from mass to moles. Now we're looking for the number of moles of zinc in a 130.8 gram sample. All right, so zinc. Let's find zinc. Zinc. I bet you guys could find it on the reference table before I can. Okay, found it. All right, zinc has a molar mass of, oh my god, 65. We're going to use 65 grams per mole. Okay. So now we're looking for number of moles, which is going to be our given sample over 65 grams per mole. Okay, 130.8 divided by 65. You should get approximately, well, let's put it in the calculator. It comes out to about 2. There's about 2.01 moles. All right, let's try this next one. Calcium phosphate. We need to find the gram formula mass. We have 3 calciums. We have 2 phosphorus and 8 oxygens. Okay. I wish I could remember these. Calcium. Okay, phosphorus here is 31. Calcium is 40 also. Wow. We get 120, we get 62, and here we get, okay, I'm gonna guess 128. Hey, I got it. Okay. Okay. 310 grams per mole. Okay. So now we're looking for a number of moles equals our given sample 77.5 grams over 310 grams per mole. 77.5 divided by 310 should get us 0.225 moles. Exactly. Alright, now we're going to get into the sort of trickier side of these calculations, and we're going to start with empirical formulas. This one's a bit of a doozy. Okay, so we need to know the percent compositions of each element before we could even derive the empirical formula. And so we're going to change each percent to mass by assuming a 100 gram sample. So you just drop the percentage and throw in a gram. Number 2, determine mole of each element by dividing mass by the atomic mass of the element. Okay, simple so far. Find the mole ratio by dividing each mole from step 2 by the smallest of the moles. And then 4, write empirical formula using smallest whole number ratio. How does this look like? Let's start with this. Here we have carbon and hydrogen. We start with 85.6% of carbon and 14.4% of hydrogen. We got to drop the percentages, pretending they are grams now, assuming we have this many grams out of 100. Okay. Now we got to divide it by their atomic masses. Carbon is 12. Hydrogen is 1. And see where they come out to. So 85.6 divided by 12, that comes out to about 7.13. Okay, 14.4 divided by 1 equals about 14.4. Okay. Now these are our ratios. So the next step here is to take each of these ratios and divide it by the smallest one to get this even further simplified. So our smallest one here is the one for carbon. So this comes out to 1, and this comes out to approximately 2. So what does this mean? This means we have now 1 carbon and 2 hydrogens. So for every 2 hydrogens, there's 1 carbon. Okay? And that's our answer. Another way you could go about this is if you go back up here to this top section. You could take these for now. And then you could try to simplify it as best as you can. Here we should also see this similar result. It's not exactly the most reliable, but it also gets you to the same sort of answer here. Alright, next example. Let's hope this is even easier to deal with. Okay. We have nitrogen and oxygen. 30.4% goes over to 30.4 grams. Here we have 69.6% of oxygen, which goes to 69.6 grams. Alright, next step is divide by their atomic masses. Nitrogen is 14 grams to figure out how many moles. Oxygen is 16 grams. Okay, 30.4 divided by 14. Okay. Gets us 2.17, and over here, 69.6 divided by 16 gets us 4.35. Alright, now there are 2 ways you could go about this. So we could go this way, 2.17 and 4.35. Alright. Looking at these numbers, you could approximate that we should get this answer, which is indeed correct. Now if we follow the other method, where you take each of these ratios, divide it by the smallest, this should come out to 1, and this should come out to about 2 as well. So this here now becomes NO2. Same answer, different methods. Alright, now here is the final topic right here, molecular formulas. So what made it different from empirical formulas? Alright, so empirical formulas require having percent compositions, whereas here we need to know the empirical formula. So we can have a molecular formula without the empirical formula. Okay, and we're going to employ these steps in this example. Here, for example 1, we have a substance with a molecular mass of 116 grams per mole. So that's for the actual molecular formula. And here is the empirical formula, C2H5. So we need to figure out a higher ratio of that. And we need to figure out what is the molecular formula of this substance. So that means we need higher ratios. Okay. So first let's start with this. We need to figure out what is the gram formula mass of that. So let's start. Okay. Over here we get 24 grams. This is 5 grams. So our empirical formula mass is going to be 29 grams per mole. Okay. So we're going to compare it here with our... So we're going to take this molecular mass divided by empirical mass. So 116 grams, because the molecular mass should always be the bigger one, divided by the 29 grams for the empirical mass. Okay, so let's put this into the calculator for a moment. I think I already know what this number is going to be. It should be 4. But let's double check. Yes, and it comes out to exactly 4. That means the molecular mass is 4 times greater than the empirical mass. Okay. Alright. So that means we're going to have 4 of these. Alright, and what does that look like now? See how we came from there? You just distribute that 4. Okay, and we should end up with this final answer. Sort of confused? Well, thankfully there's another example we could look at. Let's take a look here. What is the molecular formula of a substance with a molecular mass of that and an empirical formula of that? So first, what is the empirical formula? We have 2 carbons and 3 hydrogens. Multiply this out, 24 3, a total of 27 grams per mole for our empirical mass. Okay, so now let's put molecular over empirical. Sorry if my handwriting's getting messy. I'm just sort of rushing this. We have 54 grams as a molecular. Here we have 27 grams for empirical. 54 divided by 27 should get us 2. That means our molecular formula here is 2 times greater. Distribute that 2. And we should get C4H6. There we go. Now if you want to check, so you got to check yourself before you wreck yourself, guys. Check yourself. So let's go through this right now. We have 4 carbons and 6 hydrogens. Okay, so there's 48 over here plus 6. 48 plus 6 gets you 54 grams per mole. Hey, it checks out. There we go. Now if you notice, this is the last slide of this PowerPoint review. I hope this was helpful. Next video should be, I'm going to upload a video of the practice quiz. The 2-page practice quiz, by the way, guys. So stay tuned for that. That should come up tomorrow.